Hello class and welcome back to part 3 of the senses. We have moved on to the ears this time, and FYI I went with a cubism here for the background. That was kind of fun. Okay, so how do we memorize ear anatomy? We have 3 compartments of the ear: the external ear, which primarily is the external auditory canal, middle ear with malleus, incus, and stapes, and then the inner ear cochlea and vestibular apparatus. These are compartmentalized. These do different things, and we should come up with some little mnemonics to remember them. But first, a little fun fact: if you didn't know what was happening when your ears were popping in the airplane, well, that's your eustachian tube connecting your nasal cavity with your middle ear. It acts like a little pressure valve. Your middle ear is a compartment, and it can change in terms of outside pressure to internal pressure of your body when you go up and down an airplane, or if you dive deep into a pool. If that eustachian tube is inflamed or is having issues, it doesn't work, pressure builds up, and it can really hurt. This is why babies often cry on planes, because their eustachian tubes are not fully functioning yet, and they're more horizontal and narrower, so they're easier to stay closed, and they do not equilibrate the same pressure. That's kind of a fun little medical fact for you. Here's a schematic of what it looks like. If you have extra pressure in the external environment, such as diving deep in the pool, the eardrum is going to be pushed inward and create some uncomfortable pressure in here if your eustachian tube is closed, which is why we got to clear the ears. How do we do that, you ask? Well, there are many methods here. My favorite is the Toynbee maneuver. There are a whole bunch of other ones, FYI, Frenzel, Lowry, and Edmonds. But the combination of closing your nostrils and then drinking some water or chewing some gum or swallowing forces and compresses the air in your oropharynx posteriorly and just makes its way into the eustachian tube and just opens that right up. If none of that works, of course, you can be this guy right here. The other option is, unfortunately, get the tubes put in your ears when you're a kid, since I kept having recurrent otitis media. So let's now try to break this down into the 3 compartments of the ear and use our knowledge of anatomy and apply it to what happens physiologically, and maybe some analogies along the way. Your outer ear is sort of like a satellite dish. It really does act that way. If you ever cup your hands over your ears, your voice gets louder. If you can't really appreciate that, do that while you're whispering. You whisper and then cup your ears. You can hear your voice a heck of a lot better. The middle ear is kind of your amplifiers. It's a tiny amp, but it's a set of amps that literally amplify the sound. And the 3 bones of your middle ear, stapes is the tiniest bone in your body, can fit right on your fingertip there. And this levering system amplifies the sound, and that stapes then finally wraps or taps or knocks on the oval window, which creates some inner ear vibrations, which are now fluid vibrations that go through the perilymph and endolymph of the inner ear. Those bend the hair cells, which we're going to get to in a minute, that then create an electrical signal. So it's really neat. Sound waves turn into mechanical vibrations, which turn into fluid waves, which then finally turn into electrical signals. Here is a little schematic of it. As the sound wave goes in, it goes from outer ear in orange, middle ear, the mechanical vibrations in pink, then inner ear, which has 2. One, the fluid waves, then finally gets transmitted through the organ of Corti, which we'll talk about in a moment, the electrical signal. So this cochlea is like a curled up snail shell, and there are 3 compartments in it. If you are into Latin, we have the scala vestibula, the scala media, and scala tympani or tympani that make up the cochlea. Perhaps a little easier, the vestibular canal, the tympanic canal, and in the middle, the cochlear duct. These are filled with perilymph, as you can see here. The cochlear duct has endolymph. It's the same thing, but it's just named differently. Peri meaning surrounding, and endo meaning inner, like your endoderm and mesoderm and ectoderm. In between, there's these membranes that separate these canals, and importantly, that's where we get the vibration and the electrical signal changes. So let's talk about that. Between the vestibular canal and the cochlear duct, we have Reissner's membrane that does vibrate and shake and transmits those impulses down here. Same thing below scala tympani. And what happens in the hair cells here, we have these very specialized hair cells called the organ of Corti, and those hair cells, and quite literally hairs, are attached to this tectorial membrane, and these feel the vibrations, turns that waveform from fluid into electrical signal going along your cochlear nerve. And that is how we hear. If you take that circular snail shell and unwind it out, you have this straight long duct here. It's another way of looking at this, where the sound waves turn into mechanical vibrations or acoustic energy, which then get translated into a fluid wave and then electrical energy. One thing that this diagram does not show, we have the oval window here, which is where the stapes is, and then this waves get transmitted all the way to the round window there. So OR, oval and round, right? If you don't have good hearing, you're going to go to the OR like I did. And another thing here, endolymph versus perilymph. Final little schematic drawing out all these steps can be quite complicated ear physiology in terms of learning all the different steps and the different types of physics involved, which is why we have some ways to memorize the steps. You can go with the OMG mnemonic here, since sound gets transmitted from outer or onward, or really inward, but sound gets transmitted onward from the outer ear to the middle ear. The middle ear magnify, right? It's the amplification system, those vibrations. And then the inner ear, this is a bit of a stretch for me here. If anyone has heard of galvanic stimulation or electrical stimulation using galvanic stim, it translates via transduction into an electrical nerve impulse. So your OMG in terms of galvanic stimulation, I hope that's a good mnemonic for you. I think it kind of works for outer, inner, outer, middle. You just don't have an I for inner. It was a G. But if you have a better mnemonic, please let me know. Leave it in the comments. Send me an email through our class inbox, and I would love to spread the word to our students. This is for our, well, chart lovers, table lovers. I certainly am one of those. I love to categorize things very well. We have the region here, the main structures involved, the function in hearing. It gets a lot better if you're a physics lover, because you can now use the medium, and it's just so cool. I was very happy kind of creating this slide here, going through all the different regions, the medium from air to bone to fluid to biological, if that's a category, and then to electrical, all the physics principles involved for you physics lovers out there, and then what happens physiologically in the body. I think that's a really cool table, and hopefully a way to help you remember it. So before we move on to the next section of the ear, I'm going to leave you with a public service announcement of sorts. We now have learned that these specialized cells in your ear are quite delicate and involved, and this is why your audiologist tells you don't stick a Q-tip in your ear. The only thing that you should fit in your ear is your elbow. Like anything smaller than your elbow should not go into your ear, which means no Q-tips. Because while it might feel good, it might feel like that when you put a Q-tip in your ear, this might be what's happening, and that's not a good thing. So watch out for the old Q-tip. Okay, let's move on to the next piece of anatomy in the ear. Tucked high above the cochlea in the middle ear are our semicircular canals, and we have these in place so that when we spin and stop, we don't continue to feel like we're spinning like a salad spinner. These are, well, exactly as they say, semicircular canals arranged at right angles, 90 degrees, basically, in 3D to each other, and also have little hair cells that are triggered by movement of fluid. This is what gives you dynamic equilibrium as opposed to static, which we're going to talk about next. As you are spinning and rotating in space, my semicircular canals just activated, and then if you have a disruption, it's going to feel like you're still spinning even though you're not. If anyone's ever had vertigo, you know what's going on. So let's talk about this lag effect that the endolymph does when you spin in place, demonstrated by that little dude up here. As your body spins around, those semicircular canals spin, but the endolymph hanging out on the inside does not move because of inertia. So as you initially start to spin, the fluid pushes and bends on the cupula and the nerve cells there, triggering the electrical impulse, and you start feeling dizzy in that spinning sensation. Once the endolymph catches up, then it starts spinning with you, and then you no longer feel dizzy until someone grabs the chair and stops, and then you get that dizziness sensation because the fluid in your head is still spinning. It's similar to like the water bottle trick where you hold the water and then suddenly spin the bottle. The water stays behind due to inertia, and then eventually it'll start to move with it. And this is why spinning makes us dizzy. You can do the cool uncle trick to an unsuspecting niece or nephew when they've never had that spinning on the chair trick. You spin them around really quickly, and of course they love it, and then you grab them immediately, and then you can kind of start seeing them feel like they're spinning on the inside. If you really wanted to challenge your semicircular canal system, you can get on one of these gyroscopic chairs, which are pretty wild. That's the milder version, and then there's the NASA version where you really want to do some training so you don't get that space dizziness or space sickness that astronauts can have. So, how about a mnemonic for this? Well, maybe some people are lopsided. There are 3 different semicircular canals: posterior, anterior, or superior, I guess you could say it, and lateral, and those are detecting that rotational movement in a different plane, which is why you need that gyroscopic chair to test all 3 X, Y, and Z planes. So the anterior one is the yes, the sagittal plane going in this direction, if you're nodding your head yes. If you're shaking your head no, horizontal now. The lateral semicircular canals are being activated in me right now. And then the fun one, the posterior, that's kind of that dog-like motion to the side in the coronal plane, and that's your posterior semicircular canal. Now, there are 2 other little parts, or little sacs, so to speak, hanging out at the bottom of the semicircular canals called the saccule and the utricle. And what are those doing? This is what I was alluding to before. The semicircular canals are detecting and managing your dynamic equilibrium. The saccule and utricle are the static equilibrium components. Same thing, it has fluid and hair cells, but on top are just kind of caked on top are otoliths, which kind of act as little gravity, bags, so to speak. So as you tilt your head forward, and even if you didn't know where you were, you put a blindfold over your eyes, you kind of know that you're tilted forward because the force of gravity pulls those little ear stones or otoliths forward and bends those hair cells. So it is pretty neat that we have developed both of those systems, the dynamic for when we're moving, and then the static for when we're either tilting forward or we know we're tilting backwards because of our saccule and utricle system. So it's pretty neat. Not just the tilt where you're just in space tilting forward or tilting backwards, but also linear acceleration. So this is the feeling as you're driving forward in the car. The utricles get activated because it's the horizontal one. And then that sensation of feeling your body going upward in the elevator, that's the saccules getting activated. And this one is, I think this kind of, it's not such a mnemonic as I felt it's more of a hack. The utricle is your Uber, or utricle is your Uber ride because you're driving forward, and the saccule, you're going upstairs. I would like it to be elevator, but that doesn't work. Or maybe that gravity drop machine in the amusement parks. I don't know if one of those start with an S, but that would be a good mnemonic. If you got a better one, please let me know. I'd love to know. There are some very interesting repositioning maneuvers here when the stones sometimes dislodge, or if you just start developing this kind of sludge or junk or the equivalent of a gallstone or kidney stone in your ears, you can get what's called benign paroxysmal positional vertigo, where those stones start floating around in the semicircular canals or in the saccule and utricle and can start pushing on those hair cells abnormally or erroneously, and you're going to get the sensation that you're spinning even though you are not moving. And this is where these repositioning maneuvers come in handy. If you've heard about this, these particles are floating around, activating all these hair cells. You can tilt your head in certain positions, get it to fall into a corner or area in the semicircular canal system where it's not activating the hair cells. And this is, if you're in the clinical world, you may have seen these or heard about these. The Dix-Hallpike maneuver to diagnose it, and the Epley maneuver to, quote unquote, fix it. These are these very interesting positioning systems where you tilt your head in one position, let gravity pull those little ear stones down. You start to roll around to let those stones continue to roll around the semicircular canal, and then you come back up, and then they've now settled in a corner. It's really cool when it works. So I'll leave you with some cool little fun facts. So you can think of your semicircular canal as your carpenter's level. detecting gravity, detecting acceleration, and keeping your body level in space. Another thing we talked about, astronauts can unfortunately get a lot of confusion in their orientation because those little otoliths can float around. We don't really have gravity anymore, being able to detect that linear acceleration, which is why we do those, why the astronauts do all those various gyroscopic training sessions. And the last thing, which I think is so cool, it's not, if you've ever seen that where cats, they're falling backwards, they end up righting themselves every time. It's not magic, it's vestibular magic, the ability to spin around. They have really highly developed vestibular systems, so they are much better equipped to right themselves from a fall than humans are, which is why cats are very cool. I shall see you in the next one. If you have any mnemonics, please let me know. I'm all ears.